know it doesn't avoid the work.
Is it going to do something like that?
Yeah.
It was cool, and now you just made it.
I know. I brought your hopes up so high, and I dashed them by saying, now we still got to go through the grunt work of finding values for A, B, and C.
When choosing, I guess, an annihilator, like in your example, you have a D minus 2 and a D plus 1. Could we use either of them? Like,
Quite the contrary. I'm restricted to using D minus A, where A is a coefficient of this X.
okay.
That's why I chose D plus 1. It had nothing to do with this D plus 1 over here. It's your coincidence. I just made these examples. I forced the example to have the same thing there. So that you see I have to remove the duplicity. Do you guys agree? This is what I had before. When I first tried to solve a DE, before I discussed annihilators, I think I wrote them in a different order, but who cares? So now I got to go through the process differentiating thrice, pick everything up, slamming it back in the original DE. Do you guys mind if I don't? So you know what to do next. I don't want to walk away unless you do. All right. Okay.
No, I'm sorry, hold on.
Yes, I'll hold on.
Why ax plus bx squared plus cx cubed? Why no why is there no single constant?
You can do this if you want. And find D to come up with a number. It's just in the end, aren't you going to combine it with this first term? Excuse me, the second term. And you call that a C3.
Okay.
You could do it. It's just more work. Let's look at this example.
So how many different kinds of annihilators are there?
I just exhausted all the possibilities for you.
That's it?
So everybody, any ideas how to solve this DE? What's the first thing I should do? Eventually, I think before I dive in there, can I just first rewrite the left-hand side using differential operators? I was hoping that's what you'd say. Mike?
Oh, I was going to say solve it for the homogeneous case.
True, but you know, in the sense that when I factor that, when I actually dive in and factor the differential operator on the left-hand side, once I write it, it'll tell me exactly what my compromise solution is going to look like. So first things first, allow me to rewrite using hold it, everybody, small mistake. Sorry. I meant that to be a 2y. I apologize. Now using my differential operator notation, I think I've got a d cubed plus 3d squared minus 2d minus 1. Excuse me, minus 2. My goodness. All acting on my function y being equal to the forcing function. What's next? Well, what's next is 5. Well, actually, before I do that, can I just... You're right. I could use annihilators right away to transform this into a homogeneous DE. There's nothing wrong with that. I was just kind of thinking we should factor that column with differential operator first. And factoring. Pulling out an empty piece of scratch paper. Factoring. You can do it. You really can.
Try 1.
Why would you try 1?
Well,
Because it's easy. Because some of the coefficients is 0, so you know it's going to work. So that a 1, 3, negative 2, negative 2, and drop like a rock. Multiply, add, multiply, add, multiply, add. Look at that. So I think I now have that d minus 1 times d squared plus 4d plus 2 acting on y is equal to stuff.
on the d squared plus 4d plus 2 in order to find...
I agree. And if I use a quadratic form of factor that beast, like an r squared plus 4r plus 2, I think I'm going to get my negative b plus or minus the square root of b squared minus 4ac all over 2a. Or shall I say a negative 2 plus or minus, is that a root 2? And so I think I get d minus 1 times d minus, and negative 2 minus root 2 times a d minus negative 2 plus root 2. All right, you guys, I'm ready for you to annihilate. So to annihilate the forcing function, on the right-hand side, you're going to apply what differential operator on both sides? D squared minus 2. Minus, I couldn't hear that. Minus 4d. Plus 13. I agree. Acting on d minus 1. Acting on d plus 2 plus root 2, as I recall. Acting on d plus 2 minus root 2. Acting on y, oh shoot, look at that. Nice, clean, homogeneous dE. Piece of cake. And so can we just list our solutions? I think our solutions are going to look like y of x equals to go here first. C1. Yeah, this is why the book might not be quite as much fun as in class, because he's kind of clean and easy.
Negative 2 plus root 2. You gotta put your
E with 2x times the quantity. I get that lonely feeling a lot in class. A cosine. This is painful. 3x. Everybody okay with this? Plus b. Thank you. Sine
Oh,
3x. Oh, I think we're done. Okay. And I think I also have my complementary solution. And I have my particular solution. Well, my trial particular solution. I misspoke. And by the way, you guys, I'm running out of board space. I need a few more boards, don't I? Because now I got to use the method of integral coefficients to find those values of the compensated. Chris?
What happened to the term on the left, the quadratic?
I think the one left I use last. That generates my particular solution. My trial particular solution, I should say. And by the way, Chris, would you admit that if I use my old technique, my trial particular solution would look, oh, look at that, just like that. Because I'm looking at my forcing function. I was just using annihilators instead. Michael?
I'm confused where the d squared minus 4d plus 13 comes from.
That comes from this. I think for a forcing function that looks like this, my differential operator is going to be a d squared minus 2ad plus a squared plus b squared, where a in this example is my 2 and b in this example is going to be 3. Remember on these two boards I proved to you that this will annihilate a function of the form e to the ax times the cosine of dx. So, Michael, in other words, if ever you got e to the ax times cosine of bx, or times sine of bx, the annihilator you're going to use is that one right there. Anybody else? By the way, did you notice I didn't care about the a's and b's in the end? I just copied that one I had additional. All right.
Wait, say that again.
Yeah, I meant this. When I wrote this down on the board, you guys might have seen me looking at the board over there. I was not looking at this differential operator. I was actually looking at what the forcing function was. But you got to confess, with this differential operator, this is of the form negative 2ad, where a is 2. Well, that's what's there. This is supposed to be an a squared plus b squared, but a squared is already a 4. So b squared's got to be 9, which means b's got to be 3. But I did not do that in my head. I just looked back over there at my forcing function, identified what my trial particular solution must look like. But I had choices. So do you guys think, have I shown enough work for you guys to go home and get some practice with this? Be honest. Oh, I'm only asking because I don't like my examples. So,
Are they too simple?
yeah. So, check this out.
Okay.
Suppose y of x being equal to u of x, that's a function of x, plus, let's make this sophisticated, plus I times v of x is a solution to this special differential equation. How about a y of the nth order derivative plus next order derivative times the coefficient, excuse me. All the way down to, how about an a sub 2 y double prime plus a sub 1 y single prime plus an a sub naught is equal to, oh shoot, I'm going to write this up. How about a complex valued function, a big F of x plus I times g of x. If this up here is indeed a solution to this differential equation, then I maintain that u of x is a solution to this dE. I forgot my y. And I maintain that v of x is a solution to this dE. I'll prove it to you. You take the second differential equation, multiply both sides by I, add it together with the first, and you're just going to get this. What I'm suggesting is that maybe if your forcing function is a complex valued function, I can still solve the dE to come up with these real components. And I will maintain that I can use my u of x and my v of x as solutions to these two differential equations right here. Chris?
Isn't that kind of just an extension of the theorem of
Yes.
that says that if there is a solution y of x equals u of x plus, or f of x plus g of x, to the, or if that is a solution to, it's that without the i's.
Yes.
Isn't it just that it's
Yes, I just put the I in there, but I've got two forcing functions. It's called superposition.
Could you do that with, I think there's some system where you have three different, they're not i's, but they're like,
You mean four different quaternions?
that one.
Okay.
Can
I won't
you use
put
that for that, or?
I won't put that.
Okay. Oh, but we are doing n-dimensional vector differential equations, aren't we?
That's true, but I'm not thinking of the forcing functions as having inputs and outputs of variables that can be multi-dimensional. Because when you look at my solutions with dEs, x is just representing a real number.
Right, but eventually x will be a vector. At least in the book. Or are we not doing that?
True, but I think when I talk about solutions dEs and I use the word vector, I typically go on to think about the actual solutions to the homogeneous dE, not necessarily the input of the variable x. Big difference. So you guys check this out. Yes or no, piece of cake? If it is, let me go ahead and take a peek at the non-homogeneous case, but I'm going to look at it completely differently. I'm going to make the supposition that I got a differential equation that's complex valued. So if you don't mind, instead of using y, can I use z's? I will think of that as a z double prime minus z single prime minus 2z being equal to, how about e to the 2x times the cosine of 3x plus I times the sine of 3x. Which, by the way, means I can literally rewrite this dE as a z double prime minus z prime minus stuff being equal to e to the, help me with this, Seek Euler. 2,
2 minus 3.
how about 2 plus 3? I times x. Be there. And that being the case, you gotta check out how easy my life is to solve this DE. Because now my forcing function is exponential. Remember I have to differentiate once and twice? With my old technique, whether I use annihilators or not, the method of undetermined coefficients says when I differentiate twice, jeepers, I gotta use the product rule over and over again. Whoa, I should say that. Combination of the product rule with the chain rule. There's a bit of work involved. But you gotta confess, my life is really easy here. Because I think my trial particular solution should look like some constant times this forcing function. Let's see when I differentiate with tremendous, tremendous ease, unlike before. To differentiate, what do I get? You took too long. You're killing me.
2 plus 3i times a
2 plus 3i times a.
plus, or,
So times e to the 2 plus 3ix.
why do you have an x?
Why do you have 2a's?
I just really like a's. Big thought. The 2 plus 3i was so long to write, I forgot that I already took the a out. What's next? Differentiate again. And differentiating again, I'm simply going to get my a times
2 plus 3i squared. Or you want to
yeah, or in other words,
or
negative 5 plus
6i.
12i?
That one.
I feel so alone again. Times my e that time. Oh, but shoot, this is a method of undetermined coefficients. I still need to find the value of a. Oh, by the way, something else. It was the old technique. I had to add a sign in here. I'd have 2 constants to find. I think this is so much easier. But keep that in mind. With the old technique, I have 2 constants, so somehow this better generate a couple different values of the constants. Now, picking these 3 beasts up off the imports, slapping in the original DE, in other words, substituting back, I see that y double prime, which is this, minus my single y prime, which is this. Minus 2 times the original function, which is this, is going to be equal to my e to the 2 plus 3i times x. Now, do you guys mind if I suppress the exponential factors? Divide both sides by them because they're not going to be equal to 0. Perfectly legal. And if you also allow me to factor out my a, doesn't that give me a negative 5 plus 2i minus 2 minus 3i? Instead of minus 2, all times a is being set equal to 0. Oh, I misspoke. It's not 0, is it? My apologies. It's really a 1. Or shall I say, that leaves me with a negative 9. Is that minus I? Times a equal to 1.
Shouldn't it be negative 5 plus 12i?
Negative 5 plus 12i. Oh, you're saying I didn't write down the right number. I'm so sorry. That is a negative 5 plus 12i. Shoot. My mistake. I didn't see it. I'll change it here. What else does that change? That give me a negative 7i? Is my arithmetic okay?
I don't think so.
Yeah, I don't think so either. How about a negative 9i? Is that better? You guys, please check my arithmetic. Man, I still can't do my arithmetic. I apologize. Does that give me this? Gosh, I forgot. What does DE stand for, sensor? Math D extended? So using our math D skills. Using our math D skills.
Well, it's what's up by the conjugate.
Yep.
Or not, I guess.
Huh? Why are you multiplying by -1?
You just told me to multiply by the conjugate.
But wouldn't the conjugate? Oh, because you
Well,
factored out. You factored out a negative.
Just
Right.
make my
Okay,
face.
yeah.
And so I think A is going to be that 1/9 that I'm pulling out, times my negative 1 minus I upstairs. Oh, but downstairs, I'm going to get my 1
Negative 2.
minus I squared, which is 1 plus 1, which is positive 2?
No.
It's okay. And if it is, I better rewrite this. Does that finally give me a jeepers, a negative 1 over 18 minus 1 over 18 times I? Look at that, it's a complex number. I'll pick it up off the ink board. I'll slap it in, back into this equation, and see what the heck I generate. Because I found that my solution is going to be of the form, oh, you guys, I used y's. Shoot. Didn't I mean z's? I don't mean to be such a mess today. I mean, I'm just going to be consistent with my variables. And if that's what I meant, let me rewrite my z sub p. So, I think z sub p is going to be my a value. Times my e to the, is it 2 plus 3x?
2 plus 3ix.
Thank you. Oh, but you know what, you guys, using Euler's identity, isn't this just a shortcut for writing out this? That'd be an e to the 2x times the cosine of 3x plus I times the sine of 3x. Ah, shoot, I've got some more math D business to take care of. I've got a binomial times a binomial, it'll be a FOIL out. I'll pull out my exponential factor, and when I FOIL out, I think the first times the first gives me this. I'll slow down, I want you to see where this comes from. I think the last times the last is going to give me a positive 1/18 sine 3x. I think the inside times the inside is going to give me a minus 1/18 times the cosine of x, plus the outside times the outside, a minus 1/18 sine of 3x.
Wait, what happened to your eyes?
Oh, they disappeared. So I'll put it back in. It's just that this time I'll factor them out. Do you guys appreciate that when you look at what's on the ink board, what's above this brace is the real component of my my complex solution, but what you see above the squiggly line is the imaginary component of my complex value solution. And since the original function only involved cosines, not sines, because of the theorem I just proved the board over there, I think I'm going to grab the real component of that solution. And I will now proclaim that the particular solution to my DE and only a single variable x, represented in real numbers, is going to be that real component. Okay?
So on the, when you're foiling the outside, or the negative 18i, 1/18th I times I sine 3x, shouldn't that now not have an I piece?
Right, so I think that I squared turns to negative 1. Gives me a positive 1/18 sine 3x, which is exactly where that came from. But these two came from inside times the inside plus outside times the outside.
Okay, that was makes sense.
When you define the imaginary component, you did not underline the I. So like if you were to ask on a test to find the imaginary component of something, if you wrote that and put an I at the end, would that be incorrect?
Well, technically speaking, when I look at the imaginary component, I look at what's being multiplied to.
Would you lose points on it?
If you put it in the solution of a DE, yes. So I think my particular solution is nothing more than e to the 2x times negative 1/18, the cosine stuff, plus a positive 1/18 times sine of stuff. There's my particular solution. Now to write my final solution, I combine that with my complementary solution, and I'm in business. Chris?
I'm so lost.
Are you
just
really?
throw away your imaginary component like it was no big deal, but it's a big deal because it's right there.
What a good question. Now, don't you agree that I just committed a mathematical lie? I said, oh, look at my forcing function. Let's change this looks. Let's write it in complex form. Now, the reason why I committed this lie is because through the differentiation process, life was really, really easy. That's why I did it. But you have to confess, with this forcing function, it's only the real component. That's why in the end, I undid my lie by only taking the real component and I suppressed the imaginary component.
You
Yes, I did. I'm being sophisticated.
It's like not sophisticated, just underhanded and.
Yeah, it's really nice though. And Bryce, can I come back to something you said?
Yes.
What if this was sine of x instead, sine of 3x instead? Well, I lied to myself. Nothing changes. It's just that now I'll say that y sub p is the imaginary component, but Bryce is just what's above the square root. It doesn't multiply. You didn't like that. I said, if with my red pen, I switch this to this, nothing changes here. Nothing changes until I finally write down my particular solution. I think my particular solution as a function of x is going to be my negative 1/18 cosine of, I forgot my 3 by the way, 3x minus 1/18 times the sine of 3x, stop. No I business. That's my point. Is everybody there? I don't know if you feel it. I did a lot today. And I think it took me a long time to answer that last question. But you have to confess again, I keep saying this, but I really mean what I'm saying. I think the actual differentiation process is so much easier. Life was such a piece of cake when I committed this lie. Can I show you where this is a really big deal? I will not answer this question. Let me just pose it, and we'll talk about how to deal with it. And by the way, I promise, this will be my last question of the day. Nothing changes. Now, using my old technique to try to find the trial particular solution, my y sub p, holy cow, wouldn't that be an e to the 2x times ax squared plus bx plus c times the cosine of 3x plus e to the 2x times dx squared plus ex plus f times the sine of 3x? That's a big yikes. Because now I got to differentiate twice. I've got multiple product rules in the application of the differentiation process. Don't you guys think that would be miserable? However, using my new technique, life's a piece of cake. Well, relatively speaking, life's a piece of cake. The only thing missing from here is the factor of, well, an ax squared plus bx plus c. And I know it's a somewhat of a headache because I still, right at this stage of the game, sorry, I have to put that down here. I still think I have to use a product rule. I just think it's a lot less work. Differentiate once and differentiate twice. Notice something else. Over here, there are like 6 different coefficients to find. Now there's only 3. The only reason why there's only 3 is because I get a complex value solution. My 3 gets doubled. I end up getting the 6 original numbers. Any questions? Michael?
What did you change on the, I guess, the non-homogeneous case? Like, what did you erase on that?
I erased it because it shouldn't be there.
Okay.
It doesn't change. I meant to say z sub p equals this. So z sub p equals all of this in my box.
Okay.
I only erased because I put it in the wrong spot. I wasn't looking. All right, let's see if you guys get some pretty hefty practice with this.